Okay, so again, our goal today is to hopefully get more away from having to use limits to find derivatives by getting some more shortcuts. But before we can find those shortcuts, we need to use limits. So let me just, I'll show you the product rule that we're going to be using today. And it goes like this. If I take the derivative when I'm doing the product of two functions, then what happens is each function gets a turn as the derivative. So for example, in this piece, f is the derivative. In the next piece, g is the derivative. So this is the the product rule. And I'm going to show you guys the proof. The proof is fairly straightforward. I'm going to do it on another slide just so we have more room. But again, if you're one of those people that right at the moment you're still kind of shy away from proofs, that's fine. Just follow along. Otherwise, you can put a copy into your notes and follow along as well. But I'm going to use I'm going to use an extra slide just to have a lot of free space there. So if I'm doing it, I'm going to have to do this from the definition. So I'm going to take the limit as delta x goes to 0. And if I'm multiplying the two functions, the definition of derivative would look like this. So that's what the product of the two functions would look like using definition. Now there's one little clever trick that I'm going to throw into this to work out this product rule. And I'm going to do it in a different color for you. So this is the little sort of stroke of creative genius that helps us to prove it. So from definition, I'm going to add a couple pieces into it. So here's what I'm going to do. I'm going to subtract f of x plus delta x times g of x. But I can't just change it. I have to balance this out, right? So far I've changed the limit. If I add it back, then that would be 0. So it's even to where I started. Okay, so I've added that, what's written in black, I've added that to the limit. And let me tell you why that is a nice convenience, why it works well. I'm going to start factoring some things out of here because I don't want to see more than one piece in the limit. So for example, I'm about to factor out f of x plus delta x. I'm going to factor out g of x here. So I'll show you what it looks like once I factor it. And if I didn't add that piece, I wouldn't be able to do this factoring. So this would be f of x plus delta x and g of x plus delta x minus g of x. And then from that, I'm going to add g of x times f of x plus delta x minus f of x. Okay, so far all I've had to do, once I got past that creative addition I made in black, all I've had to do here is factor out. Okay. Now some of you at this point might recognize where we're headed. You might say, oh, that looks a little bit like, and then when you recognize something that looks familiar, you can pull it out of the limit. I'm going to cut this into two pieces now. This plus sign, I'm going to make two limits, so it'll be a little easier for you to see the pieces. So this will be the limit as delta x goes to 0 of f of x plus delta x. And I still have this fraction here, but that's okay. Some of you might recognize this fraction by now. And then I have another piece here. So does anybody recognize where this is going now? I hope somebody does. Anybody recognize anything in there? There's two things you should recognize by now. Yeah, Danny.
The big bracket one, that itself, it's a derivative.
Yeah, so the big bracket is a derivative. Oops, sorry, too far. So for example, the big bracket's here. What will we call that? Somebody murmured it. Kara, was that you? Nope. Well, this is the derivative of g. So I could rewrite this as the limit as delta x goes to 0 of f of x plus delta x. And this is the derivative of g. Over here, this is the definition of derivative for f. So this is the limit as delta x goes to 0 of g of x times f prime of x. So now, as delta x goes to 0, that means I just have f of x times g prime of x plus, well, there's no delta x's in here, so it would still be g of x times f prime of delta x. So you can see each one gets a turn. Here it's g, here it's f. Each one gets a turn as derivative. So that's how it goes from definition down to what we call the product rule. Okay, so that's our one proof for the day. We'll stick to one proof a day, I promise. Okay? So now that we have this new rule that we should be able to use, I would like to see if you can apply it. So here's 3 questions. There are products in the first one. We could call this f, and we could call this g. See if you can apply the product rule pattern. If you feel like you're confident enough, keep going. There's 3 others to try. Okay, so the way I like to think about it is everyone gets a turn as the derivative. So in the first one possible way to do this is we'll take the derivative of f first. So that'll be negative 4x. Then I'm going to take the derivative of g so that everyone's had their turn. Derivative of g would be 4. Okay. So if you're on the right track, it could be like you added the pieces in a different order, because obviously addition and multiplication, they could show up in a different order, but those are the pieces we should all have. Okay. For the next one, again, if everyone takes a turn, then if x is going to be the derivative in the first one, it'll be 1 times e to the x plus x times your favorite derivative, e to the x. Okay, so there's derivative number 2. And for the last one, there's a product here. And then the other one is something like we talked about last day. So let's see how we do with the trig ones. Take turns as derivatives. This will be 2 times the cosine of x plus 2x times the negative sine of x. And so far all I did was this one piece here. I haven't done the whole thing. So now I have to take away 2 times the cos of x. So if I collect some like terms, that leaves me with negative 2x sine x. Hands up if 2 out of 3 you could handle there. You found the product rule for at least 2 of them. Okay. So again, I know it gets overwhelming that you have all these rules, but remember that the goal is to get proficient so that the rest of the course will keep using them. So you will get used to finding the rules and you won't have to memorize them. We'll be using them until May when your AP exam comes up. So you may already have this suspicion, but I will go ahead and confirm it. You can extend the product rule. I'm not going to prove it. I know I said one proof a day, right? But everyone gets a turn. So the same thing would happen is it would be f of x, take the derivative, then I'll take the derivative for g of x. and then take the derivative for h of x. Okay. So see if you can handle, there's 3 products here in this next one. I'll give you a minute to see if you can work out its derivative. Okay, so if everyone takes a turn, then you may have come up with something like this. 2x sine x cos x plus x squared sine, sorry, I'll back that up. I'll do them in order. Okay, so that would be the product rule with those 3 pieces. Now, today when we do our notes, we're not going to simplify our derivatives. I'll assume that you can simplify on your own. I'm just interested in getting the calculus part across. So here I would probably simplify this if it was a test. But today, just for the sake of, spending time in calculus and not algebra, we won't do our simplifying. So the other rule you're going to learn today is the quotient rule. Now the quotient rule is pretty similar, but there's some more fractions involved, obviously, because we're talking about quotients. So I'm not going to do the proof, but it is in your textbook if you'd like to see it. And what happens for the derivative of f of x over g of x is you now end up with, and in this time the order does matter, it's the derivative of the top times the bottom, subtract the top times the derivative of the bottom. And in that process of working with those fractions, we end up with a common denominator of g of x squared. So it doesn't look all that friendly, and it's not. It's one of the least friendly of our rules. But in the grand scheme of things, it's never been an issue by the time we start working with it. I know it looks frightening now, but you'll get practice. It's never been an issue when it comes down to the tests and the other things. But that's it for today, product and quotient rule. Okay, so let's try it on the first one. We'll see how it goes. It's going to be the derivative of the top. Okay, so the derivative of the top would become 5 times the bottom, subtract the top times the derivative of the bottom, which is 2x. And it would be all over the bottom squared. So again, I'm not expecting you to simplify your calculus work for me, unless it's a test or a quiz, because then I do want to see your best answer. But in your homework and when we do our notes, just for the efficiency of spending time on calculus and not algebra, you don't need to simplify it. Okay, so I'll let you try the next one on your own, see if you can figure out quotient rule there. Okay, so for this one, my suggestion was sometimes it's worth simplifying first to make life a little easier. So if I multiplied this by x over x, we talked about this when we were doing those trig identities in Math 12. If I multiply through, I get a lot simpler of a fraction. Now it's a little easier to work with. So again, the pattern is it will be the derivative of the top, so 3 times the bottom. Take away the derivative of the bottom, so this time it'll be 2x plus 5 times the top, and the bottom squared. So as you can see, that the quotient rule is not necessarily the nicest one to work with because there's fractions, and it's a little trickier to remember than the product rule. So sometimes rather than working with the quotient rule, it can pay to simplify. So for example, you get into autopilot and you see something like 9 over 5x squared, and your brain says, oh, that's a fraction, that means quotient rule. It'll still work if you do the quotient rule, but there's just a lot simpler ways to answer this question. So that's what I want you to think about for these next 2 examples. See if you can simplify it first before you worry about using the quotient rule. Okay, so in the first example, if you were to rewrite this, I would have written it as 9 over 5 x to the negative 2. That would have a derivative of negative 18 over 5 x to the negative 3. And there is no need to use the quotient rule. That's just simple power rule like we talked about last day. In the next example, if I was to take a look and just see what would it look like if I distributed, well, this is what I'd have. And usually if you have a monomial denominator, like one term denominator, it's usually easier to think about simplifying. So for example, if I split it into pieces, it would be negative 9 over 7 plus 6 over 7x. That would have a derivative of just 6 over 7. So there wouldn't be a need again for the quotient rule.